Namaste students, welcome back to my channel. Students, in our previous video, we have studied about a new term that is the hybridization. We have studied about the main points of the hybridization and the basic concept of the hybridization. Now, on the basis of the hybridization, we'll find out the shapes of the different molecules. We'll study the shapes of different molecules in two parts. In first part, we'll find out the shape of those molecules which are surrounded by only bond pairs, and in second part, we'll find out the shape of the molecules which are surrounded by both bond pair as well as the lone pair, but on the basis of the hybridization. So today in this video, we'll study the shape of the molecules. We'll study that how we can find the shape of the different molecules which are surrounded by only and only bond pairs. So we'll start with BEF2. We'll start with BEF2. We'll start with BEF2, and today our topic is shape of molecules. Shape of molecules having only bond pairs. Having only bond pairs. Now here it is BEF2. So obviously BE is the central atom. So BE, first of all, I'll write the electronic configuration of BE in the ground state. GS means ground state. So first of all, I'll write the electronic configuration in the ground state. Now the BE electronic configuration is 1s2, 2s2. Means in BE the valence shell. In BE the valence shell is 2. The valence shell is second one, because according to hybridization, the valence shell electron will participate in the bond formation. So it is 2s and 2p. Why I am writing 2p? Because if we have second shell, so obviously we have 2p subshell, but because it is empty, therefore in the configuration we will not write 2p, but here I write 2p. So 2s, 2. Why opposite sign? Because in an orbital, two electrons don't have the same spin. That's why one is clockwise and another one is anti-clockwise, and 2p is 0. 2p is 0. Now fluorine is approaching to beryllium. Fluorine is approaching to beryllium. When fluorine will approach beryllium, what happens? Force of attraction increases. Due to the increase in the force of the attraction, an energy is released. And that amount of energy is utilized to excite the electron from of beryllium from S to P. Now, what is the need of the excitation? Because here we have two fluorine which are attached with beryllium. Now, if two fluorine are attached with the beryllium, and if we apply the orbital overlap concept of valence bond theory in hybridization, then this beryllium should have two half-filled orbitals. The beryllium should have two half-filled orbitals, but in the ground state, beryllium don't have any half-filled orbital. So that's why when fluorine will approach beryllium, what happens? The amount of energy which is released, that amount of energy is used to excite the electron from S to P. So in this way, we'll get another state which is known as ES, that is the excited state. GS is the ground state, ES is the excited state. Now in excited state, one of the electron from S jump to P. As a result of which we get two hybrid orbitals which we get two atomic orbitals which overlap with the fluorine. Now, because both the bonds which are formed in BEF2 have same energy, so what happened? There is a formation of the hybrid orbital. So these two orbitals, one s and one p, these two orbitals will mix these two orbitals mix with each other, as a result of which there is a redistribution of energy between these two orbitals, and we get two new orbitals which are known as hybrid orbitals. Because in hybridization we have studied that number of hybrid orbital is equal to the number of the atomic orbitals which are combined during the bond formation. So beryllium in the hybrid state, I have two hybrid orbitals. The name of these two hybrid orbital is sp, 2sp, and here are the two unhybridized p orbitals. These are unhybridized. Now in these hybrid orbitals, the electrons will fill according to the same rule which we have studied in the filling of the orbitals in atomic orbital, like Pauli exclusion, Hund's rule, and Abhau principle. Now these hybrid orbitals behave as a degenerate orbitals. What are degenerate orbitals? Orbitals of same subshell which have same energy. And in those orbitals, the pairing will not occur till then all the orbitals will singly fit. These are the degenerate orbital, and we have studied the rule of filling of degenerate orbital, that is the Hund's rule of maximum multiplicity. So they also behave as a degenerate orbitals because they have same energies, they have equal energies. That's why the filling of electron will according to the Hund's rule of maximum multiplicity. Now we have two electrons, so one electron will go in one sp orbital and another electron will go in another sp orbital. Now fluorine will reach to beryllium. Now if I write the electronic configuration of fluorine, it is 1s2, 2s2, 2p5. So fluorine has one half-filled orbital, and that is the p orbital. So this p orbital overlap with the sp hybridized orbital, and the second p orbital of this second fluorine that combines with the overlap with the second sp hybridized orbital. So here we get one electron of fluorine. So here fluorine and here fluorine, and the bond which is formed between the beryllium and the fluorine, the name of that bond is spp sigma bond. spp sigma bond. Why spp sigma bond? Because beryllium sp orbital is there and fluorine p orbital is there. That's why it is spp. And first bond which is formed between any two atoms is a sigma bond. That's why it is spp sigma bond. So the hybridization is sp, and we have studied in our hybridization that whenever we have sp hybridization, then the shape or geometry of the molecule should be linear. So its shape becomes BeF2 with a bond angle of 180 degree. So in this way we can find out the shape of the BeF2. Now we'll find out the shape of other molecules. Second molecule I'll take, that is BF3. Now first of all I'll write the ground state configuration of boron. Boron in the ground state. What is the configuration of boron? 1s2, 2s2, 2p1. So again the second shell is the valence shell. So I'll write the only valence shell, that is 2s and 2p. This is 2s2 and this is 2p1. Now three fluorines are approaching to boron. It means boron should have three half-filled orbitals. And that three half-filled orbitals we will get when one of the electron from S will jump to P. And that jump will occur when the fluorine comes close to boron. At that time the energy will release, and that type of energy is utilized by the boron to excite its electron from S to P. So in the excited state, in the excited state, we get 1s and 2p. 2s1 and 2p2. Now I have 3 orbitals which have half-filled electrons. Now these 3 half-filled orbitals combine with each other, redistribute their energy, and results in the formation of 3 new hybrid orbitals, and the name of those 3 new hybrid orbitals will be sp2. sp2. So in the hybrid state, in the hybrid state, these 3 orbitals combine to form 3 hybrid orbitals which are known as sp2, and 1 p orbital remain unhybridized. This remain unhybridized. Now, because sp2, all 3 orbitals have same energy, so they behave as a degenerate orbitals. So the electron will fill according to the Hund's rule of maximum multiplicity. Here we have 3 electrons. So 3 electrons will fill one by one. 3 electrons will fill one by one. 1, 2, and 3. Now the 3 fluorine will approach to boron. 1 fluorine, 2nd fluorine, 3rd fluorine. Fluorine, fluorine, and fluorine. And the name of these bonds is sp2p sigma bond. Why sp2p sigma bond? Because the sp2 orbital of B overlap with the p orbital of F to form the sigma bond. And because the hybridization is sp2, the geometry should be triangular planar. So the geometry is BF3 with a bond angle of 120 degree. Now we'll study the hybridization in another molecule. Third is CH4. Third is methane, CH4. So first of all, we have to write the ground state configuration of carbon. So carbon, the ground state configuration is 1s2, 2s2, 2p2. So the second shell is the valence shell. So I'll write 2p, 2s2 and 2p2. 2s2 and 2p2. Now, how many hydrogen are approaching to carbon? How many hydrogen are approaching to carbon? 4 hydrogens are approaching to carbon. It means we should have 4 hybrid orbitals. We should have 4 atomic orbitals in the carbon which are singly filled. But in the ground state we have how many? We have only 2. We want 2 more. So by the excitation of 1 electron from here to here, we get 4. And this excitement will occur when hydrogen will approach to carbon. At that time the energy released, and that energy is used to jump the electron from S to P. So this is the ground state configuration. If I talk about the excited state configuration, it is S1 and P3. S1 and P3. Now, how many orbitals I have now? 4 orbitals I have, and each orbital is singly filled. So these orbitals will combine with each other, redistribute their energy, and results in the formation of 4 new set of orbitals which are known as hybrid orbitals. So in the hybrid state, it becomes like this. 4 sp3 hybrid orbitals. 4 sp3, 1s and 3p, they combine with each other to form 4 new hybrid orbitals, and the name of those 4 new hybrid orbitals is sp3. And these are behave as a degenerate orbitals because they have same amount of energy. Now if I fill the electron 1, 2, 3 and 4, now when hydrogen will approach, then first hydrogen, second hydrogen, third hydrogen and fourth hydrogen. Hydrogen, hydrogen, hydrogen and hydrogen. Now, if I write the electronic configuration of hydrogen, it is 1s1. It means s orbital of hydrogen combines with the sp3 hybrid orbitals of carbon to form the sigma bond. That's why the name of these bond is sp3 s sigma bond. sp3 s sigma bond. sp3 s sigma bond. And because the hybridization is sp3, due to sp3 hybridization, its shape becomes tetrahedral. So the shape is like this: C H H. One is above the plane and another one is below the plane with a bond angle of 109.5 degree. And this is tetrahedral. Now, fourth is PCl5. Now, if I write the electronic configuration of phosphorus, the electronic configuration of phosphorus is neon 3s2 3p3. 3s2 3p3. Clear? It means the valence shell is third. In phosphorus, we have third valence shell. Now, if I write the ground state configuration of phosphorus, it is 3s2 3p3. Clear? Now, how many chlorine were approaching to phosphorus? 5 chlorine are approaching to phosphorus. So, we want 5 such orbitals which have half-filled electron, but we have only 3. Now, if electron will jump from here to here, we will get 3 only. So, what happened? Now, it is third shell. In third shell, if we talk about the quantum number, n equals to 3. If n equals to 3, the value of L varies from 0 to n minus 1, that is 2. It means 0, 1 and 2. 0 stand for S, 1 stand for P and 2 stand for D. It means in third shell we have D subshell also. So here we will write 3D also. So while filling the electron in the electronic configuration, we have studied that 3D will fill after 4s because the energy of 4s is less than that of 3D. But during hybridization, during bond formation, the electron will jump from 3p to 3d, not from 3p to 4s. Because what is hybridization? Hybridization is the intermixing of the atomic orbitals which have very slight difference in their energies. So there is a very big difference between the energies of 3p and 4s. So the electron will not jump from 3p to 4s. Yes, it will jump from 3d to 4s, but not from 3p to 4s. So 3s, 3p and the electron will jump in 3d. But the next electron will fill in 4s. That is different thing. Filling of an extra electron, that is different thing. And excitation of the electron which is already present in the atom, that is the different thing. So what happened? One of the electron from P will jump to D and one of the electron from S will jump to P. So as a result of which in the excited state we get 3s1, 3p3 and 3d1. Now I have 5 such orbitals which have half-filled electrons. Now these 5 orbitals combine with each other, redistribute their energy and form 5 hybrid orbitals. So in the hybrid state, I get 5 hybrid orbitals. 5 hybrid orbitals, and the name of these 5 hybrid orbitals is sp3d. 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 Now, if I fill the electron 1, 2, 3, 4, 5, and if I write the electronic configuration of chlorine, it is neon 3s2 3p5. So the 5 orbital will overlap with these sp3d orbital 2, 3, 4 and 5. 1 chlorine, 2nd chlorine, 3rd chlorine, 4th chlorine and 5th chlorine. And the name of the bond is sp3d p sigma bond. P sigma bond. And in our VSCPR or in hybridization, we have studied that if the central atom is surrounded by 5 bond pair and the hybridization is sp3d, then the shape is trigonal bipyramidal. So the shape is PCl5. These 3 are in one plane. This chlorine is above the plane and this chlorine is below the plane. Means if suppose my hand is a plane, in the center I have phosphorus, 1 chlorine, 2nd chlorine, 3rd chlorine are present in the form of triangle. 1 chlorine is above the plane like this. 1 chlorine is above the plane and the other one is below the plane. Clear? So triangular bipyramidal. Why bipyramidal? Because if I draw a line, if I join the line of this chlorine with the next 3 chlorine, then I got a pyramid. Similarly, lower pyramid. So trigonal bipyramidal. Now in this, the bond angle between these electrons, the bond angle between these bond pair is 120, and in this it is 90 degree. If we talk about the bond angle which are present in the plane, the bond angle is 120 degree. And if I talk about the bond angle between this and the plane, that is 90 degree. Now, if the bond angle is less, then what happens? If the bond angle is less, the electrons are close to each other. And if electrons are close to each other, there is a possibility of repulsion. So what happens? The bonds which are present in the plane, they repel the bonds which are present above and below the plane. They repel the bond which are present above and below the plane, because here the angle is 90 degree. The bond angle is less, as a result of which repulsion is more. Therefore, they repel the bond angle. They repel the bonds which are present above and below the plane. As a result of which, the bond length of all PCl5, is not equivalent. The bond of all PCl5 bonds are not equivalent. Why these are not equivalent? Because in the plane, the bond angle is 120 degree, and above the plane, below the plane, that is 90 degree. Due to less bond angle, due to small bond angle, there is a repulsion. Due to repulsion, the chlorine which are present in the plane, they repel the chlorine which are present above and below the plane, as a result of which the bond length which is present above and below the plane is greater than the bond length which is present in the plane. And the chlorine which are present, the bonds which are present in the plane, these bonds are known as equatorial bonds, and the bonds which are present above and below the plane, these are known as axial bonds. So these two are known as axial bonds. And these 3 are known as equatorial bonds. And the bond length of axial means axial PCl is greater than the equatorial PCl because of the bond angle difference. But if we talk about PF5, If here it is PCl5, here it is PCl5, but in this we have an exception, that is PF5. If we talk about PF5, in TF5, all the bond angles have equal distance. All the bond angles have equal distance. Clear? So PCl5, this is the hybridization, and on the basis of the hybridization, the shape is trigonal bipyramidal, but due to the difference in the bond angle, the bond length of the axial and the equatorial PCl is different. Now we will study the next molecule. Fifth is SF6. First of all, I write the ground state configuration of sulfur. Now if I write the electronic configuration of sulfur, it is neon 3s2 3p4. It is 3s2 3p4. It means the valence shell is third, and in third valence shell we know that we have D subshell also. So if I write, then here it is 3s2 3p4. Now because 3p is a degenerate orbital, so filling of electron will, according to Hund's rule of maximum multiplicity, 1, 2, 3 and then 4. And 3d 0. 3d is 0. 3d is 0. Now, how many half-filled orbitals we want? 6 half-filled orbitals. And how many we have? 2. Now, if one electron from P will jump to D, how many half-filled orbital will get? 4. But how many we want? 6. So, S electron will also jump. So, in the excited state, it becomes 3s1, 3p3 and 3d2. 3d2. 3s1, 3p3 and 3d2. And 3d2. Now, in the hybrid state, these 6 atomic orbitals will combine to form 6 hybrid orbitals. 6 hybrid orbitals. 1, 2, 3, 4, 5 and 6. And how many electrons we will have? 6. So 1, 2, 3, 4, 5 and 6. And the name of these orbitals is sp3d2. sp3d2, and the 3d unhybridized orbital remain as such. Now fluorine will approach to sulfur, and fluorine require only one electron in the p subshell, in the p orbital. So p orbital will overlap with this orbital and to form sp3d2 p sigma bond. Fluorine, 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 fluorine and fluorine. And the name of bond is sp3d2 p sigma bond. And because the hybridization is sp3d2, the shape is square bipyramidal. The shape is square bipyramidal, and it is like this: S, F, F, F and F. Here it is a square. In a square we know that the bond is 90 degree above the plane, below the plane, and here the bond is also 90 degree. And because the bond between the equatorial and the axial bond angle is same, therefore the bond length is also same. So in SF6, all SF bonds are equal in length. Unlike PCl5, all the bonds in SF are equal in length. They are equal in length, and the shape is square bipyramidal, because this fluorine is above the plane, means towards you, and when I join this fluorine with these 4 fluorine, I get a pyramid. So that's why it is square bipyramidal. One pyramidal above the square and other pyramid is below the square. That's why square bipyramidal. Now we will study the shape of IF7, and I believe that before me you can predict the hybridization of the IF7 molecule, IF7. Now the configuration of iodine is krypton 5s2 5p 5. Krypton 5s2 5p5. It means the valence shell is fifth shell. So if I write here iodine configuration in the ground state, it is 5s2 5p5 and 5d0. 5s2 5p5 and 5d0. Now how many half-filled orbitals I want? 7. I have only one. When one electron will move here, I get 3. When this electron will also move, I get 5. And when this electron will move, I get 7. So in the excited state, the configuration becomes, and from the starting I told you that the electrons will move only at the time of the bond formation. This we have studied in the hybridization, that hybridization will never occur in the isolated atom. It always occurs during the time of the bond formation, because the energy which is required to excite the electron will we get during the time of the bond formation. So 5s1, 5p3 and 5d3. 5d3. So 5s1, 5p3 and 5d3. Now in the hybrid state, all these 7 orbitals combine to redistribute their energy and to form 7 new hybrid orbitals. So in the hybrid state, we have 7 orbitals. We have 7 orbitals. The name of these orbital is sp3d3, and each of these orbital have one unpaired electron, and the 2d orbital are unhybridized. These 2d orbitals are unhybridized. Now the fluorine will approach to iodine. 1, 2, 3, 4, 5, 6 and 7. 1 fluorine, 2nd fluorine, 3rd fluorine, 4th fluorine, 5th fluorine, 6th and the 7th. And the name of each of these bonds is sp3d3 p sigma bond. sp3d3 p sigma bond. And the shape is I, F, 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 F and F. That is a pentagon and bipyramidal. Here the angle is 90 degree and here the angle is 72 degree. So again there is a difference in the bond angle, and due to the difference in the bond angle, all the IF bond length is not equivalent. All the IF bonds are not equivalent due to the difference in the bond angle. So whenever there is a difference in the bond angle, means the bond length are not equal, and whenever all the bond angles are equal, it means all the bond length are equal. Clear? Now I'll give you some molecules and you tell me that what is the hybridization in that molecules and what is the shape. So here are the molecules: HgCl2, BCl3 and CCl4. In these 3 molecules, you have to calculate, you have to find out the hybridization, and then with the help of the hybridization, you have to find out the shape of these molecules and you have to draw these molecules also. So I'm waiting for your answer. Tell me your answer. I'll see you in my next video with the second part of this topic, that is the shape of the molecules having both bond pair as well as the lone pair.